This is a short video on how we name and write ionic compound formula units. So ionic compounds are those compounds that are held together by electromagnetic force. So they're composed of a positively charged cation and a negatively charged anion. The way I always learn to remember this, and I know it sounds silly, but cats have paws, so cations are positive. That's just the way I learned it. So this is solely an electromagnetic connection, kind of like two magnets held together. They're not physically bound to each other. You could bind two magnets together with a piece of paper between them. So if you get a larger electromagnetic force, you could pull them apart. As it is, outside of an external electromagnetic field, they are very, very stable bonds. So how do we determine what a formula unit is? First off, the formula unit is the lowest whole number ratio for ionic compounds. It is the way you write ionic compounds. You write them in terms of formula units. What you're looking for is the lowest whole number ratio of the ions that gives you a zero net charge. So let's look at some examples. So I've got four sets of ions here: sodium plus chloride, magnesium plus chloride, potassium plus sulfide, and barium plus nitride. Notice each of these has a number and a sign beside it. The sign indicates whether it's positive or negative charge. The number is what order of charge it is. This is in terms of the fundamental charge unit we talked about way back in chapter 2, the charge of one electron or one proton. Again, remember, you can't change the number of protons in an atom. So sodium plus 1, it means it has one fewer electrons than it does protons, right? Chloride has a -1, which means it has one more electrons than it has protons. You're changing the number of electrons when you make ions. You're not changing the protons in any way. So what we're going to do is we're going to combine these together in a way such that I get a zero net charge. So let's look at the first one. Sodium plus 1, chloride minus 1. So in a 1-to-1 ratio, I would have a charge of 0. Plus 1 minus 1 equals 0. Now let's look at the second one. Magnesium plus 2, chloride minus 1. Obviously 1-to-1 isn't going to work because I would have a charge of plus 1, right? Plus 1 minus 1 equals plus 1. So I'm going to need 2 chlorides to make this a zero net charge. So my formula would be MgCl2. Now note the 2 in subscript. Again, if there's only one of them present, you don't need a subscript. But anything more than one, you need a subscript. And we're looking at the lowest whole number ratio. So yes, I could get a zero charge with magnesium 2, chloride 4. But that wouldn't be the lowest whole number ratio. So that wouldn't be an appropriate formula unit. Okay, let's look down at the next one, potassium and sulfide. Potassium has plus 1, sulfide has minus 2. Here, similar to the second one, I've got a 2-to-1 balance. But the metal, the cation, is the one that has the 1. So now I'm going to need 2 of the metal and 1 of the non-metal. Good thing to remember. Ionic compounds are those formed between metal and non-metal. All right. Easiest way to identify them, with one exception we'll get to in a minute. Now the last group down here, barium and nitride. Barium is plus 2, nitride is minus 3. At first it's like, ooh, how do I balance those two? It's really pretty simple. Look for the lowest multiple they share. 2 and 3. The lowest multiple it shares is 6. So I try to get each of them to a charge of 6. So if I have a plus 2, I want to get it to a plus 6, I would have to multiply it by what? 3, right? Now I have a minus 3, and I want to get it to a minus 6. What do I have to multiply it by? 2. Therefore, my formula is Ba3N2. Now I have plus 6, minus 6, total charge is 0. Okay, the next group we have what we call polyatomic ions. Polyatomic ions are ions that are composed of multiple atoms, but they operate as one unit, all right? Almost exclusively, these are negatively charged anions, right? Almost exclusively. The only non-metallic cation we're going to work with is the ammonium ion, which is NH4 and has a +1 charge. Other than that one, the only ones we're dealing with, negatively charged polyatomic ions, but works the same way. So here I've got a set of polyatomic ions with metals. So in this first one, I've got sodium +1, and the second one, NO3, is nitrate. So that nitrate as a group, all right, not individual atoms in it, but as a whole, operates as one unit and has a -1 charge. So just like I did with sodium and chloride, I would treat it the exact same way. +1, -1. So my formula would be that. Now you get down to the second one. Here, just like the last time where I had magnesium and chloride, I have magnesium with a +2 and nitrate with a -1. I'm going to need 2 nitrates. Well, I need to designate that I need 2 of the entire group, not 2 of any individual component in it. So the way I do this is I put the group in a parentheses and then put a subscript for how many of the group I need. This is not the same as writing Mg2O6. That's something very, very different. This is magnesium nitrate, and I've written it with the 2 out there to denote I need 2 nitrate groups. All right. Down here we've got the potassium and sulfide, and as you know, it would be the same way, K2SO4. If I only need one of the group, I don't need the parentheses. And put the last one in, same idea as last time. Barium +2, phosphate -3. So we're going to get the barium 3, and then I need 2 of the phosphates, so I put the phosphate in parentheses. Note, a little thing that drives me nuts that students do all the time, and I know why you do it, because you're trying to remember the charges and stuff like that. You only write the charges if they're in their ionic state, if you could actually detect the charges. When they're bound together in formula units, you cannot detect the charge, so it is not appropriate to write the charge. Note that in the individual ions, I have the charge. But over here, I don't. I don't have the charge. So how do we name the ionic compounds? Ionic compounds are named by simply putting the anion first, followed by the cation. This is going to be all we need to do. The charges are explicit. We know that sodium is always +1. We know that nitrate's always -1. So we don't have to tell how many they are. It comes from the charge interaction. So if I take this, I know sodium's +1, I know nitrate's -1. The only formulation that I can get from the name sodium nitrate is the formula above it. And that's the key to nomenclature. Nomenclature, you should have one and only one meaning possible. So when I say sodium nitrate, I know that means, okay, it's ionic because I have a metal and a nonmetal. So I look at the charges. Sodium is +1, nitrate is -1, so my formula has to be NaNO3. That's it. That's the only way you can interpret that name. Therefore, it's the only name you can give to that formula unit. Going down, let's look at this one. Potassium +1, sulfate -2. But I just name it potassium sulfate because by the name, potassium is +1, sulfate is -2. By definition, it has to equal 0 charge. So I'm going to need 2 potassiums for 1 sulfate. So K2SO4. Same thing holds true here. Even though I need 3 bariums and I need 2 phosphates, it still gets the name barium phosphate. All right. So naming ionic compounds is pretty simple as long as you know the names of what you're looking at. The polyatomics are what drive people nuts. They always forget the polyatomics, so work on those a little bit. Now, one little quirk we got here. So the metals we've talked about so far have one and only one possible charge. That's actually unusual. Only group 1 and group 2 elements for the most part have a single charge state, right? So potassium's always +1, barium's always +2. outside of group 1 and group 2 on the periodic table, there are only 4 other elements in the metals that have a single charge state. That's silver, cadmium, zinc, and aluminum. That's it. And you do need to know what the charge state of those 4 elements are. Aluminum's +3, zinc and cadmium's +2, silver's +1. All the other metals have a possibility of multiple charge states. So since this name has to be explicit, we have to say what the charge state is. So take, for example, this one. This is copper, Cu, and it's nitrate. Now, looking at the formula, we can tell what the charge of copper is, because none of the anions have more than one charge state. So the nitrate's always -1. So if this is the appropriate formula, that means the copper has to be +1 for this to equal a charge of 0. So that means we would name it copper 1 nitrate. All right, so look at another example. Here we've got Fe, which is iron, and sulfate. So we know sulfate is +2. I've only got one iron counterbalancing it, so the iron must be, or sorry, sulfur is -2, so I only have one iron counterbalancing it, so the iron must be +2. So I would name it iron 2 sulfate. Note, the numbers that I put there are in Roman numerals. All right, so let's make it a little harder. So Pb, if you go down your periodic table, is lead. Sulfate, -2. I got 2 of them, so I have a total charge of -4. I have 1 lead, so it is going to be lead 4 sulfate. This is something that trips students up all the time. The most common mistake they do is they look at this number when I write it out and they say, oh, that's how many of them I have. So I'll get this for like iron 2 sulfate, I'll get Fe2SO4. No. The number is the charge on the metal, right? So iron 2 means it's iron 2 plus. Lead 4 means it's lead 4 plus, right? What I'm doing is I'm explicitly stating what the charge on the element is. So when I say copper 1 nitrate, there's only one way to interpret that. I have copper, which is +1. I have nitrate, which is -1. So it must be CuNO3. All right. Hopefully this helps you out a little bit with naming ionic compounds for lab report 4 and also for unit 2. I will talk to you guys later.